Okay, we were looking at this scatter plot, and we drew this potential line of best fit here in red. And we're looking at the relationship between horsepower and miles per gallon. So we noted that there is a moderate negative linear relationship between horsepower and miles per gallon. So, as horsepower increases, miles per gallon decreases. And we determined that using this correlation of negative 0.78 and looking at our scatter plot, we can see this negative relationship. But as we said, we want to use linear regression to create this line of best fit, to perform prediction, to create this red line that we have drawn. So the way we said we were going to do that is linear regression. So let's first just back up and recall from back in the day, Algebra 1. So Algebra 1, the equation for a line. And the equation is y is equal to mx plus b. So hopefully that looks vaguely familiar. You might have to go deep into your memories for this. But b is the y-intercept, and m is the slope. So I just drew an example here. So we can see that on this plot, our y-intercept right here is at 1, positive 1. And so that's why in our equation, maybe I should rewrite it. So y is equal to, we have some slope plus 1. So that's where the 1 comes from. And then our slope, if you recall what slope is m is equal to rise over run. So rise over run, so let's see, to go from 0, 1 up to 2, 2, let's do rise over run. So how far did we rise? Well, we only rose by 1, right? We increased by 1, but to do that, we went over 2. So that's why I have 1 for rise, because we increased by 1 value, and we went over 2, which is why run is equal to 2. So when we look at the equation for this line, we have 1/2 x plus 1. So y is equal to 1/2 x plus 1. So we're going to take this idea and carry that forward into regression for the equation for a line. So we're going to follow this idea to perform simple linear regression. So here's our formula. yi, so recall y is just our value of the response variable or the dependent variable. Beta naught is going to be our intercept, so this is equivalent to our value of b. So b here, that's our beta naught for our intercept, plus beta 1 times xi. So xi was the value of the explanatory variable, and beta 1 is the slope variable. So beta 1 is our m value from up here. And then plus epsilon I, this is just some random error, because our line's never going to be perfect. There's going to be error. And so we need to account for the fact that we will have error in our regression line. So I've just written these things out. So again, yi is the response variable. So the response for observation I. Recall I is just the indicator or the index from 1 to n. We have n observations. I is just the ith observation from 1 to n. Xi is the explanatory variable for observation I. So this is just our actual observed data. So we download some data set, or when we're working on our homework, we're going to have some data set. these xi and yi values are our actual data. So recall that we want to explain values of y using x. I'm going to get rid of some highlighting here. Okay, so can we explain y with x? So those are our actual data values. But then there are things we're going to need to estimate, those being the slope and the intercept. So beta naught is our slope. Or sorry, beta naught, beta 0 is the y-intercept. So we can interpret that as that it's just the value of y when x is equal to 0. Right? If we go back up to this example, the value of y when x is 0, so when x is 0, the value of y is equal to 1. So that's why our y-intercept was 1. Okay, now let's talk about beta 1. So beta 1 is our slope. So it's the slope of our line. The way we can interpret that, it's the change in y per unit change in x. So it's just rise over run, right? For every unit change in x, y is going to increase by however much. So in this example, when x increased by 1, y only increased by 1/2. Which means when x increases by 2, y increases by 1. So that is what's going on with our slope coefficient. Okay, now let's move on to our error terms, or error term rather. So epsilon I, it's just random error in y for observation I. So this is unobserved randomness. We might think that there's some relationship between horsepower and gas mileage. And we might have some linear relationship between the two, but there's always going to be randomness, right? Even if we take the same car and take two different cars that have the same horsepower, there's going to be differences. And that might be explained by other factors, right? One might be more aerodynamic than the other. But even the same car, if we measure the gas mileage over and over again, there's going to be differences from sample to sample. We know that that's just due to sampling error, unobserved randomness. So we just have to take into account the fact that our linear relationship is going to be imperfect. And then finally, I is equal to 1 to n, and that's just to remind ourselves that we have n observations in our data set. So recall that in all our previous chapters, we discussed our population parameters and sample statistics. So recall that just how we used x bar and p as our estimates for the population parameters, mu and pi, right? We used x bar as our estimate for mu, and we used p as our estimate for pi. Mu and pi are population parameters, x bar and p are our sample statistics or our estimates for those. So we're doing the same idea here. So in this case, our population parameters are beta naught and beta 1, and we're going to use b naught and b1 as our estimates. So when we think about the true relationship between x and y, that relationship is explained by the beta parameters, beta naught and beta 1. But whenever we get an actual set of data and we try to estimate those things, we're going to call them b naught and b1. So thus, our equation that we're trying to estimate, so this is the same equation as above, this one right here. So our actual value of y will be explained by some population intercept plus population slope times the explanatory variable plus the true randomness in the population that we can't account for. So we're going to estimate that with yi hat. So yi hat is our estimated or predicted value for y given x. So it's our actual predicted value from our estimated regression line. And it's going to be equal to our estimate for the intercept, which is b0, plus b1 times our data xi. So this is our actual regression equation. This is what we are estimating. We are predicting values of y. Again, our predicted values we're calling yi hat, and it's equal to our estimated regression equation, which is b naught plus b1x. This is what we are trying to estimate.